we've been given this giant hunkin'-looking equation. As you can see over here, we've got x plus y quantity squared minus x minus y quantity squared equals x to the fifth plus y to the fifth, and we're asked to find dy dx. Now, if you haven't heard of the term implicit differentiation before, you might start freaking out, because you're like, well, the only way I can differentiate is if it's defined explicitly as a function of y, such as y equals x squared, but I can't really do that here. In fact, it's probably near impossible to get y by itself when there's so many y's in the equation. And you'll remember that we can differentiate this function implicitly, right? This function right now is defined implicitly. It's defined implicitly. So we can still find, remember, we can still use our property that d dx of y is simply just dy dx, and we're used to solving for, in these videos, I've always been solving dy dx as the red color. So we want to find a dy dx somewhere in here. Remember, by differentiating y, we'll find a dy dx, and then we'll solve for dy dx in order to find the derivative of this expression. Equation. It's not an expression, it's an equation. Pardon me. My bad. So let's go ahead and see if we can do that. Let's see if we can differentiate this whole equation. Well, naturally, a great place to start is obviously by applying. We're going to take the derivative of both sides. Oops, didn't mean to do that. The derivative, come on. Okay, I will not do it with my fingers so that it doesn't get mad. The derivative with respect to x on this side, and I'm going to go ahead and remove the fact that this is an implicitly defined function. I'm just going to get rid of all that and then make that black. We're going to, again, we're going to take d dx. We're going to take the derivative. Nope, not dx dx. It's just simply d dx. Take the derivative of both sides. And what's going to happen? Well, we're going to end up taking the derivative of this whole thing. So what's that going to look like? Well, this first term, I notice, is going to imply the chain rule because we have a function, x plus y, or at least we have some form of an equation, within this raised to a certain power. So we're going to notice that this is the outside function and this is the inside function. When we go ahead and, excuse me, let me go turn off my cell phone really quickly. So anyways, as I was saying, we have a chain rule with the outside function, the inside function. So when we take the derivative, we're going to take the derivative of the outside. So we're going to bring the 2 power down front. We're going to multiply it by whatever's inside. The inside is not going to change. So this x plus y, that's not going to change. And then we're going to multiply it by the derivative of the inside. And the derivative of the inside is an addition problem. You know, or the derivative of the sum is the sum of the derivatives. So the derivative with respect to x of x, that's simply just 1. And the derivative with respect to y of x, or derivative of x with respect to y, that it is simply dy dx. And everywhere I write a dy dx, since that's what we're solving for, I'm going to write that in red since we're used to solving for dy dx in red. Then we're going to go ahead and subtract, and we have another chain rule with the same idea where we have our inside function being x minus y and our outside function being a quadratic. So we're going to do the same thing. We're going to bring the 2 down front. The inside is going to remain unchanged, and then we're going to multiply by the derivative of the inside. Again, the derivative of 1 is just 1, and the derivative of negative y is negative dy. Oh, again, dy dx we're writing in red. The negative will keep there, but the dy dx, that's a sloppy dy. The dy dx we'll be writing in red, as we can see there. And then, so that's the left side of the equation. And then we're going to equal, well, what's the derivative with respect to x of x to the fifth? We're going to bring, it's a power rule, so we're going to bring the power down front. So we'll bring down the 5 times x to the n minus 1. 5 minus 1 is 5x to the fourth. Now for the y to the fifth, we notice that there's another chain rule, because remember, y is a function of x, so y itself is a function as opposed to x, which is just the independent variable. So we actually have an outside function being y raised to this power, being this function of x raised to a power, in the inside being a function of x. So then we're going to add that to, We're going to bring the 5 down front. The inside remains unchanged. We're going to reduce the power by 1, so it'll be y to the 4th times the derivative of the inside and the derivative of y with respect to x. I keep saying I'm going to write it in red and then never do it, because that's simply dy dx. So now I'm going to go ahead, I'm going to do a bit of algebra, and I'm going to switch to, maybe I'm going to simplify, because these are all well, I'll simplify in yellow, because why not? So I'm going to go ahead and distribute the 2x through, so I'm going to get 2x and 2y times the 1 plus the dy dx, and then we're going to subtract I'm going to distribute the 2 through. I'm going to get a 2x minus 2y times the 1 minus dy dx. And now on the right side, I don't think that there's much simplification we really need to do. It's simply just 5x to the 4th plus 5y to the 4th, again, dy dx. Now, when going about these problems, the easiest way to solve a differential or an equation where we're differentiating implicitly, notice that in our previous video we had simply just 1 dy dx, but in this equation we have 1, 2, 3 dy dx's. We'll count them again. We've got 1, 2, 3 dy dx's. So in order to solve, the easiest way how can we make 1 dy dx? Well, I mean, think about what we do when we have a quadratic. When we have a quadratic, we have something like x cubed, or maybe a cubic function. We have like an x cubed plus an x squared plus an x. Well, how do we get there to be just 1x? Well, we could factor out a factor of x, and that would be x squared plus x plus 1. And then we could divide by all that business, and we'd be just left over with that x. We're going to do the same thing. We're going to get all the dy dx's on one side of the equation, and then factor out that dy dx. So let's go ahead and do that. What would happen if we were to factor out that dy dx? Well, first we have to get all the dy dx's on one side of the equation, and I'm noticing that we're probably going to want to simplify this a bit more. So I'm going to notice that we can do a bit more distribution. So I'm going to continue to do that distribution. We're going to get 2x plus 2y plus 2x plus 2y times dy dx. Right? All I did is I simply distributed the 2x 2y to the 1, which we can see right here, and the 2x 2y to the dy dx, which we can see right here. And then I'm going to go ahead and I'm going to do the same thing, distribute likewise again, and it's going to get me, not the same thing, but it's going to get me something very similar. And I'm going to get I'm going to get a 2x minus 2y minus a 2x minus 2y dy dx. And that's going to really help us. That's going to really, I know that looks very, very ugly, but that's going to really help us get our differentials, our dy dx's, all on the same side of the equation now that they're all factored out. So let's go ahead and see if we can make that happen. So I'm noticing I'm going to go ahead and put all the dy dx's on the left side of the equation and all the non-dy dx's on the right side of the equation. So the dy dx's on the left side of the equation, we can see them right here, and right here. So I'm going to want to get everything else onto the right side of the equation, or in this case, move it to the left side of the equation. So I'm going to get a 2x plus 2y. We're going to need a lot of space. I'm going to write over here. A 2x plus 2y times a dy dx. And then we're going to keep the minus, we're going to keep this minus 2x, or I guess I'm going to want to distribute, if I were to distribute the negative through, we could get rid of these parentheses here. And then I didn't even have an end parenthesis there, so that would be a negative, and then this would be a plus as that negative would distribute through. So we would have plus 2x minus 2y dy dx minus, I'm going to subtract this 5y to the 4th dy dx to the other side of the equation, minus 5x to the 4th dy dx. All of that is going to equal, everything else we didn't use is going to go to the other side of the equation. So we have a 5x to the 4th plus a 2x minus 2y minus a 2x plus 2y. And we can go ahead and simplify this bad business. Well, first off, I'm going to go ahead, while we simplify, I'm going to scroll down so we have a bit more room. We can now factor out a common factor of dy dx. And if I were to do that, that's going to leave me with the rest of this junk. 2x plus 2y plus 2x minus 2y minus 5x to the 4th equals 5x to the 4th plus 2x minus 2y minus 2x minus 2y. And now we can go ahead and maybe we can do a bit more simplification while we're at it. We want to get dy dx, and on the inside of this giant parentheses, we're going to have a negative 5x to the 4th. I'm going to do it by highest power. 2x and 2x, that is a 4x, and 2y minus 2y, that means there's just no y's. And that's going to equal a 2x minus a 2x. That means we're going to get a 5x to the 4th. There's going to be no 2x's, but we're going to subtract a negative 2y minus a 2y. That is a negative 4y. And then again, we want to get dy dx. We want to get dy dx by itself. That's what we're solving for. We're solving for what is the derivative of that equation. So in order to solve for it, we're going to simply divide by negative 5x to the 4th plus 4x on each side. Negative 5x to the 4th plus 4x. And if we do that, that's going to cancel, and that's going to cancel. And we are going to be left with dy dx equals 5x to the 4th minus 4y over negative 5x to the 4th plus 4x. Let me make sure that's the solution. So I made a pretty big mistake as I'm going back over my work. I'm noticing that I should have had a 5y somewhere, and that somewhere for where there should be a 5y, I'm going to go ahead and delete it. It should be right there. There should be a 5y right there. And so I think what ended up happening is I think I just missed, I think that, let's see, let's go back and trace our steps. And when we go back, this is a good lesson to learn, that when you make a mistake in calculus, go back and check your work and see if you can find where we went wrong. And I think it's in this step right here. I wrote down the 5y to the 4th, but it looks like that 5y to the 4th didn't carry over. This x is supposed to be a y. I'm going to write that maybe in blue. I'm just going to write over. I'm not going to delete it. That's supposed to be a y. So then this is supposed to be a y. And then this is supposed to be a y. Therefore, this is a y. And therefore, this is a y. And that's why I ended up getting the wrong answer. So I just dropped a y. So if you guys were confused, I'm really sorry. Humans make mistakes too, and it's hard to own those mistakes, especially when it's on the internet and everyone's supposed to trust and believe you. So I apologize for that. But that is the correct answer now. Now that we got the y's in place, that is the correct answer. And that was a very hard implicit differentiation problem that we happily worked out and got the right answer.